Hello everyone, myself Shamli, Assistant Professor at SVC. I've always been fascinated by how machines can be taught to see and interrupt the world around them, much like human do. Today we are going to dive into the topic, the exciting and rapidly evolving field called a computer vision, a branch of artificial intelligence that enables the computers to understand, analyze, and process the images and videos. So, without further ado, let's go into the topics. So, today we are going to step into the last unit of this topic, the image based rendering and recognition. Imagine you are trying to create a 3D movie scenes or any virtual tour where you can move the camera anywhere, but without actually recording from every angle. How is that possible? That's where the image based rendering comes into the play. In this unit, we step into the fascinating world where images are not just static pictures but built-in blocks for immersive visual experiences. We will explore how techniques like view interpolations and layer depth images helps generate a new viewpoint from the existing photos. Then we move into more advanced concepts like light fields and lumigraphs, which capture the full light information of a scene to produce lifelike renderings. You'll also learn how computers or the environment matters, and video based renderings brings dynamic realism to digital content, a foundation for applications in virtual reality, film productions, and 3D reconstructions. The second half of the unit shifts towards the image based recognitions, teaching computers to see and understand what is an image. We will uncover how algorithms detect objects, recognize faces, and even classify them into categories or instances. We will also dive into context and scene understanding, where machines interpret entire environment rather than isolating the objects. Finally, we will discuss the recognitions database and test sets, the essential data sets used to train and evaluate the visual recognition systems. So, by end of this unit, you will understand how images can be both the input and the output of intelligent systems and forming the bridge between the visual perceptions and artificial intelligence. Now we can go into the topics. Introductions to image based rendering and recognition. Image based rendering and image based recognitions are two key areas in a computer vision that bridges the gap between the image processing, computer graphics, and artificial intelligence. Together, they focus on how images can be used not only to recreate the realistic visual scenes but also to analyze and understand the context within them. The image based rendering refers to the process of generating the new views of a scene directly from existing images without requiring a detailed 3D models. Instead of constructing the geometry, the hybrid techniques used to capture the images and manipulate them to simulate the different viewpoint. Methods such as viewpoint interpolations, layer the depth images, or light fields and lumigraphs, which enables the creativity of an highly realistic virtual environment. So, the dynamic backgrounds and any immersive visual experiences. The HBS plays a vital role in virtual reality, a 3D movie productions, or any video games, and any AR, VR, augmented reality, where the realisms and speed are essential. On the other hand, the image based recognitions deals with the capability of machines to identify and categorize the visual content It involves detecting objects and recognizing the faces, identify the specific instances, and understanding the entire scenes based on the contextual informations. The techniques in these areas allows the system to perform the object detections, face recognitions, instance and category recognitions, and scene understanding. The tasks that are foundational to application like autonomous vehicles, security systems, medical images or imaging, and smart assistant. In essence, the image-based rendering helps computer to generate visually accurate scenes, while image-based recognitions enables them to interpret and understand what they see. Together, they represent two sides of the modern computer vision, one focused on a visual creation and other on the visual comprehensions, so shaping the future of intelligent visual technologies. So this is how it's going to work out. In today's world of immersive digital experiences like virtual reality tools or any cinematic visual effects and advanced surveillance systems, image based rendering, that is IBR, has become a more powerful techniques for creating the realistic scenes directly from real images instead of some complex 3D models. Unlike the traditional graphics method that relies on the geometry and lightning creations, so the IBR uses to capture the images from a multiple viewpoints to synthesize the new perspectives of a scene. This makes it possible to move around in a photograph or generate the smooth transition between the different camera angles, a process known as the view interpolations. The techniques such as layer depth images, that is LDI, light fields, and lumigraphs enhance the realisms by preserving the scene's depth and lightening details while environment matters. So it helps to integrate the virtual objects seamlessly into the real world videos of crucial for applications like film compositing and any augmented reality. On the other hand, the image-based recognitions focuses on the teaching computers to interpret and understand visual content. It encompasses the object detections, face recognitions, instance recognitions, and category recognitions, all aimed at enable the machines to identify what or who appears in an image. Combined with the context and the scene understanding, these methods empower the intelligent system that can analyze the traffic scenes, which performs the medical image diagnostics, or enable the facial unlock features in a smartphones. Together, image based rendering and recognitions bridge the gap between the visual realism and visual intelligence, forming the backbone of a modern computer vision applications. So, by studying these concepts, learners gain a insight into how machines not only reproduce the visual world but also the comprehend it. So this IBR and IBREC, that is image based rendering and image based recognitions, are two key areas in a computer vision that bridges a gap between the image processing, computer graphics, and any artificial intelligence. So together they focus on how images can be used not only to recreate the realistic visual scenes but also to analyze and understand the content within them. So, this IBR refers to the process of generating the new views of a scene directly from the existing images without requiring a detailed 3D models. Instead of constructing the geometry, IBR techniques uses to capture the images and manipulate them to simulate the different viewpoint. Methods such as view interpolations, layered depth images, light field, and lumograph, as we mentioned before, which enables the creations of highly realistic visual or any virtual environment. So, the dynamic backgrounds and immersive visual experiences. Here, IBR plays a vital role in a virtual reality, a 3D movie productions, or any video games, as well as in a augmented reality, where realisms and speeds are essential. On the other hand, this IBR, image based recognitions, deals with the capability of a machine to identify and categorize the visual content. It involves detecting objects, recognizing the faces, identify the specific instances, and understand the entire scenes based on the contextual information, as well as the techniques in these areas allows the system to perform the object detections, face recognitions, instance and category recognitions, and the scene understandings as a task. So these tasks that are the foundational to applications like autonomous vehicles, security systems, medical imaging, and any smart assistants. So, in essence, image based rendering helps computers to generate the visually accurate scenes, while image based recognition, that is IBR, enables them to interrupt and understand what they see. Together, they represent two sides of the modern computer vision, one focused on visual creation and other on the visual comprehensions, shaping the future of intelligent visual technology. So here the IBR creates new view. So basically what the intro about this is that the IBR creates a new views from the real images, like a synchronization, and it avoids explicit 3D modeling or any geometrical reconstructions. It's always relies on captured images instead of any polygonal models. So it produces realistic visual experiences, which uses interpolation between the real viewpoint. What is the main key idea here is to render in by reusing these pixels, which enables a photorealistic visualization by use in VR, AR, or any virtual tools. It's often combined with the depth informations, light fields, and any lumigraphs. That is a core technique used in this. So it also enables the dynamic scenes visualizations and foundation for the immersive visual medias. So this is all about the intro to this IBR. Next we can move to the next topic. Principle of image based rendering. The principle of image based rendering, that is IBR, revolves around a simple yet powerful idea. Instead of building a complete 3D model of a scene, we can use the real images captured from a multiple viewpoint to recreate a new or unseen perceptives. In traditional computers graphics, every pixel of an image is generated from a virtual 3D models using a geometry, lighting, and texture informations. In contrast, IBR bypasses this complex process by relying on the actual light rays recorded in a photographs. So by understanding how the appearance of a scene changes with the different viewing angles, the systems can interpolate between the captured images to produce a smooth transitions and the realistic rendering. The core of this principle lies in the sampling and reconstructing the light field, a concept that represents how light travels through space in every directions. When multiple images are taken from a different viewpoint, each image essentially captures a small portion of this light field using techniques like view interpolations, depth mapping, and pixel reprojections. A new images can be synthesized as if they were taken from the intermediate camera position. This makes the rendered output not just visually accurate but also photorealistic, which is preserving all the natural lighting, shadows, and any reflections of the original scenes. In essence, image based rendering transforms the raw image data into a flexible visual models of the real world. So, it bridges the gap between the photography and the computer graphics, allowing us to move through the visual environment without the need of the or extensive geometric modeling. This principle is what powers many immersive technologies today. So, from virtual reality work through the 3D telepresence to video based rendering in modern film productions, which is giving the viewers the illusion of being there, even though the scenes exist only as a collections of the captured images. So, working mechanism of this image based rendering begins with the acquisitions of the multiple images of a scenes from a different camera position, as we discussed before. So these images are usually captured using the control condition to ensure the consistent lighting and exposure. So each image represents a unique views of a same environment, and together they forms the foundation of the rendering processes. So the system then extracts the correspondence informations between the images, identifying which pixels or the feature in one image matches those in the others. So this step is crucial as it helps to estimate the depth or disparity the map. So which describes how far each object in the camera is from. So once the depth information is available, the rendering engines uses the view interpolations techniques to synchronize the new viewpoint. So this involves the reprojecting the pixels from the original images onto a virtual camera plane corresponding to the desired viewpoint. If the new viewpoint lies between two existing cameras or position, the system blends the corresponding pixel from both the viewpoints. So creating a seamless transitions basically. The advanced methods like LDI, layer depth images, further enhances this process by storing the multiple depth layer per pixel, allowing for more accurate handling for occlusions, where one object partially hides another. In more complex setups, the IBR employs the light field or lumograph representations that captures not just color and depth, but also the full 4D informations of light rays in a space, their positions and directions. This enables the generations of any possible views of the scenes without explicitly modeling the geometry. So additionally, technique like environment methods and video based rendering integrate the dynamic element such as reflections, moving objects, and lighting variations, bringing scenes to life with realism and fluidity. Finally, all the process data is blended and rendered using a pixel based or image wrapping algorithms, producing a new images that looks as though it was genuinely captured by a physical camera at the viewpoint. So the result is a visually convincing rendering that maintains all the intricate details like color tones, shadow, and perceptual distortions of the real world scenes. Now, let's discuss about the advantages, limitations, and the real world applications of this IBR. So, the greatest advantage of image based rendering lies on the ability to produce highly realistic visualized scenes without requiring the complex 3D models. Since the images used are captured directly from the real world, the resulting renderings retain the natural lighting, textures, as well as reflections. It is details that are difficult to replicate using the traditional computer graphics. The IBR also offers computational efficiency in certain scenarios as it bypasses heavy geometric modeling and rendering the pipelines. This makes it especially useful in virtual reality, augmented reality, and film productions, where lifelike visuals and smooth transitions between the viewpoints are essentials. Another major advantage is that the IBR can easily integrate it into the existing images or video datasets, allowing for rapid scenes reconstructions using 1D cameras rather than expensive 3D scanners. However, the IBR also comes with its limitations. Its accuracy and realism depends heavily on the quality and the number of input images. If the captured images do not cover all viewpoints adequately, the artifacts such as blurring, ghosting, or missing textures may appear during the interpolations, which is handling the occlusions, that is, where one objects eye the other, is particularly challenging, especially when only a few camera angles are available. Moreover, because IBR relies on a real world images, it struggles with the dynamic scenes, involves moving as well as incorporating the depth estimations when an object changing lighting conditions or any reflections. The computational complexity can also increase when the depth estimations and the multi-layered images representations, so making the real-time rendering difficult for a large-scale environments. Despite these challenges, the real-world applications of image based renderings are vast and transformative. In the entertainment industries, the IBR is used for a special effect and virtual cinematography, allowing the filmmakers to generate a new camera angle without reshooting the scenes. In virtual tourism and culture heritage preservation, the IBR helps to create immersive 3D tours of any historical sites using only photographs. It can be used in any types of work of archaeology, many things. It also plays a crucial role in a medical visualization, telepresence, and remote sensing. So basically, where realistic scenes reconstructions improves, understanding and interactions plays a major role. With advancement in a deep learning and neural rendering, with the modern IBR systems are now capable of a synthesize ultra-realistic images from the minimal input data, bridging the gap between the captured reality and the virtual experiences. So basically in this topics, we have discussed about the 2D images from a different viewpoint and construct an overview. Basically it captures the 2D images from the real camera and converted into a 3D view in a more realistic way. But it is limited by the viewpoint coverage also. So that is the main idea behind this principle of the image based rendering. Next we move to the next topic of this unit. The view interpolation is one of the fundamental techniques in image-based rendering, which is designed to create a new in-between views of a scene from a set of the existing images taken at a different viewpoint. The core idea is similar to how our brain perceives the depth and continuity when our eyes or head move slightly. We don't need to see every possible angle. Our mind fills in the gaps smoothly. In the same way, view interpolations generate a virtual viewpoint between two or more real camera positions, producing a seamless and realistic visual transition. The process begins with the two or more reference images captured from a slightly different positions for each point or pixel in these angles. The algorithm finds correspondence points that represent the same feature or object in both the views. Once these correspondences are identified, depth informations or disparity between the images is estimated. This depth data allows the systems to wrap or reproject the pixels from the original images into a new viewpoint. Finally, by blending the wrapped images, the system produces a synthetic images that look as if they are captured from the camera or the physical camera placed exactly between the original ones. Mathematically, this involves pixel interpolations and geometric transformations that align the source images of the new viewpoint. The closer the desired viewpoint is the one of the original images, the more the influence that image will have in a final blend. The advanced method also handles occultation, that is where the part of the scenes are visible from one view but hidden in the another. To avoid ghosting or missing the area in the synchronized views, the view interpolation is widely used in applications such as 3D movie effects, virtual reality navigations, video conferencing, and panoramic image creations, where smooth transitions between viewpoints enhance realisms and emotions. It plays a crucial role in creating lifelike virtual experiences without requiring the expensive 3D models or extensive rendering computations. In simple terms, the view interpolations gives us a power to look around in a scene, even from a viewpoint that were never actually photographed or captured, making it a cornerstone of the modern image based rendering systems. So, basically, in this topic, we have covered the core techniques in IBR and generate the intermediate views between the captured frames based on the geometric and intensity interpolations, which requires the known camera positions also. It wrap up the maps pixels from one view to another, with the depth maps refines interpolations accuracy, blend in multiple views, ensures continuities, which handles the occultations using the depth orderings. So this image morphings used for smooth transitions where the epipolar geometries aligns features across the images. It is used to stereo visions and multi-view the rendering, which supports the slow motions and viewpoint animations. It also reduces the needs of the dense camera setups, efficiency in panoramic image synthesis. So the real-time interpolations possible with the GPU, which requires a correspondent estimates between the frames, also enables a virtual camera fly thoughts. So this is all about this topic. We'll move to the next topic. First topic we are going to see is that view interpolation is a powerful and widely used technique in computer vision and computer graphics that enables the generation of new images or viewpoint from a collection of photos taken at a different camera position. Essentially, it allows us to create smooth, continuous transition between the existing images, giving the illusion of moving through a scene from perspectives that were not originally captured by any cameras. So this capability is invaluable because it significantly reduces the need to capture or model every possible viewpoint in a 3D space, which would otherwise be incredibly time consuming or computationally expensive. At the heart of a view, the interpolations lies the challenges of blending the multiple images while preserving the two key consistencies. The geometric consistencies and photometric consistency shapes the consistency meaning ensuring the objects in the scenes maintain the correct shapes and position relative to each other at the viewpoint changes. The preventing the unnatural distortion or wrapping. The photometric consistency involved keeping colors, shading and lightening natural across the view. So the resulting image look realistic and coherent. To achieve this, the view interpolations often employs techniques such as mesh-based modeling or image wrapping, which rely heavily on accurate depth information for each determining the exact position, orientations and intrinsic parameters like focal length of each cameras when the image were captured. Without this precise calibration, the interpolant views can suffer from blurring, ghosting, or geometric distortions, which break the illusion of a natural viewpoint transition. The viewpoint interpolations and as many practical applications. In VR, that is a virtual reality, it enables a user to explore the immersive environment freely, moving seamlessly between the viewpoints to enhance a sense of presence. In telepresence system, it allows the remote participant to feel as if they are physically located in a distant place by navigating the video's feeds naturally. Additionally, interactive virtual tours in real estate or the museum exhibit use view interpolation to let users walk through the spaces smoothly without any physical being there. A very familiar real world examples of viewpoint interpolation in Google Sheet or Google Streets views. When you use the street views to move along a street, the system uses an interpolation to blend the photos taken at different spots, creating a continuous, smooth visual experience that stimulates the walking or driving down the road. Despite its benefits, view interpretation comes with the challenges. One major issue is handling occultations part of the scenes hidden behind other objects, which can cause gaps or inconsistencies in the synthesis view. The variations in lighting between the input images can also create visual artifacts like flickering or unnatural shading. Moreover, the process can be computationally intensive, especially when dealing with the high resolution images or a large number of input views. To overcome these hurdles, view interpolations techniques are often combined with the depth sensors that provide accurate 3D informations or advanced method like light field rendering, which captures and use a dense angular informations about light rays in a scene to generate even more realistic novel views. In summary, the view interpolations is a vital tool bridging the gap between the static photography and a full 3D reconstructions. It enables the explorations and interaction with the complex scenes in a visually compelling, efficient manner, enriching user experience in a gaming or the VR, or we can say also the teleprints and many other field too. Next topic we are going to see about the LDS, the layered depth images are an advanced technique for representing in 3D scenes that goes beyond the traditional depth maps. While a standard depth map stored just a single depth value for each pixel, essentially recording the distance to the nearest visible surfaces. The LDS stores multiple layers of depth and corresponding color informations per pixel. This means the LDIs capture not only what is directly visible but also the surface hidden behind those visible parts, known as the occluded surfaces. Layer depth images. So this LDI, that is a layer depth images, are an advanced representations used in a image based rendering IBR to store not just the color information of a scene but also the multiple depth values along each viewing rays. Unlike a normal 2D images, which records only the visible surface of object, and LDI captures what lies behind those surface as well. In other words, it stores the several layers of colors and depth for each pixels, representing both the visible and hidden part of a scene. The main idea behind the LDAI is to handle the occlusions, situations where one object hides another from a particular viewpoint. In traditional rendering or a simple depth maps, only the closest surface is recorded. So, when you try to generate a new view, hidden regions may suddenly becomes visible, but there is no information available to fill them in. So, leading to holes or missing pixels. LDA solves this by storing the multiple samples per pixels, each corresponding to a different depth along the same line of the site. So this allows the renderer to peel away layers and reveal the background surface when needed. So ensuring the smooth and a complete view interpolations. So to create a layer depth image, multiple camera images are combined, and for each pixel, all visible and particularly occluded surfaces are captured along the viewing rays. During the rendering, when the viewpoint changes, the system reprojects these layered samples to synthesize the new view. Because each pixel carries more than one layer, the LDA enables more accurate handling of parallax, effect, and depth continuity and transparency, and resulting in a far more realistic visual transitions between the viewpoints. In practical applications, LTAs are widely used in a virtual reality, 3D reconstruction, video-based rendering, and telepresence system, where maintaining the visual consistency and realisms during the movement is crucial. That allows the user to navigate smoothly through the complex scenes while preserving the fine visual details that would otherwise be lost. In short, the layer depth images extended the traditional image based rendering by giving each pixel a depth memory, allowing the scenes to appear natural and complete, even when they viewed from angles that they were never originally captured. It's like giving every pixel the power to remember not just what it sees, but what is hidden just behind to it. Light fields and lumigraphs are advanced concept in image-based rendering that captures the complete flow of light in a scene, allowing the computers to generate highly realistic images from the arbitrary viewpoints. Without building a full 3D models, the fundamental idea is that if you know how light travels through the space in every directions, you can reproduce any possible view of the scene by sampling these light information. A light field represents the intensity and color of the light rays in a 3D space, parameterized by their origin and the directions. Instead of storing the images from just a few viewpoints, a light field captures all rays passing through a region of a space. This means that once a light field is known, the scene can be rendered from any viewpoint or camera position with correct perspectives, so shadings as well as in occlusions effects. Light fields are particularly powerful for view interpretations as they provide continuous visual informations between a captured image, enduring the smooth and realistic transitions. The lumigraph is a related concept proposed as a more practical way to implement the light field rendering. While light field captures a full 4D representations of a light in a space, Lumigraph stores a discrete set of images along with the geometric information such as a depth or a camera position to approximate the light field. This makes the system more efficient rendering, storage and computational requirement while still enabling the high quality noble view synthesis. So the lumigraphs are particularly useful when combined with the techniques like image wrappings and reproductions, allowing the dynamic reconstructions of the complex scenes with fewer input images. So both a light field and a lumigraphs eliminates the need for a full 3D modeling, relying instead of a real world capture data. So they handle the occultations, parallax, and perceptive changes naturally, which is producing the photorealistic rendering that are difficult to achieve with the traditional graphics. The applications includes virtual reality tools, cinematic effect, telepresence systems, as well as interactive 3D visualizations, where users can move freely and see the environment from any angle while maintaining the realisms. In essence, the light fields and lumigraphs give computers a way to see like humans, just capturing not just surface but how light interact with the entire scenes. They represent a bridge between the real world photography and virtual scenes generations, forming the backbone of modern image based rendering systems. Let's see some of the example for layer depth images. Imagine you are photographing a street scenes with a car parked in front of a building. In a normal 2D images, each pixel records only the visible surfaces. So you capture the car in a front and the part of the building visible behind it. If you try to generate a new view slightly to the side, the area of the building that were eaten behind the car will appear blank or distorted because the original images has no information about them. This is when the layer depth images comes into the picture. In an LDI, each pixel stores multiple layers, the colors and the depth of the car that is a foreground, and the color and the depth of the building that is a background. So behind to it. So when you generate a new viewpoint, the systems can peel away the car layer to reveal the building behind it. So filling in areas there was previously eaten pattern here. So the result is a smooth, realistic view of the strength from a new angle without holes or missing textures. So another everyday analog, think of like a stack of transparent sheets, each painted with an object at a different depth. Looking through the stack from one angle shows one arrangement, but shifting your viewpoint reveals the objects behind the front layers. So the LDIs works in a similar way, storing the depth layer per pixel to handle the occultations and created the realistic noble views. So the topics we have covered in this LDI is that first, it stores a multiple depth layer per pixel and captures the visible and hidden surfaces, which extends the traditional depth image concept and also used to rendering the novel viewpoint of that particular pixels here. So each layer contains the colors as well as the depth values, which allows to correct occultations and lanes, which is efficient for scenes with a partial transparency derived from the multiple stereo images, which improves the realisms by including the background detail, which enables the view extrapolations. So basically here, it simplifies the 3D reconstructions pipelines to use in a virtual reality and telepresence. This LDS compressions reduces the data latencies and also used in the parallax mapping for realisms. So these are the topics we have seen in this, we have covered for that. So it can also be combined with the light field, and some other things will be on more depth that we can see in the upcoming topics. Light fields. A light field is a powerful concept in an image-based rendering (IBR) that describes all the light rays traveling through the every point in a space in every possible direction instead of capturing just flat 2D images. A light field captures the complete visual informations of a scene, including how light varies with both positions and directions, and this makes it possible to reconstruct a new viewpoint, adjust the focus, and even changes the viewing angle all after the image has been captured. In simple terms, a light field tells us what color of light passes through each point in a space and which directions it travels. Mathematically, it is often represented as a 4D functions like L of u, v, s, t, where u, v represent the position of the light rays and s, t represent its directions. By sampling this light field densely using multiple cameras or lens arrays, we can simulate how the scenes would look from any viewpoint without explicit modeling 3D geometry. Example of light field is that imagine you are looking at the flower vase on a table. You take many photos of it from a slightly different position, left, right, up and down. Each photo captures light rays coming from the vase from a slightly different angle. When all these images are combined, they form a light field dataset. Now, using this dataset, you can create new views, as if a virtual camera is moving smoothly around the vase. You can even refocus the image to make the front petals sharp and the background blurry, or vice versa, because you have informations about how light changes with directions and position. This principle is used in light field cameras like electro camera, which allows you to refocus your photo after capturing it. It is also used in a virtual reality, augmented reality, and holographic displays, where light fields data helps to create immersive realistic visualized experiences by reproducing the true depth and parallax. To summarize this, the light field represents the total flow of a light through space, capturing every ray's position and the directions, allowing us to generate realistic, geometry-free rendering of a scenes from any viewpoint. About the lumigraph, a lumigraph is a powerful technique in image-based rendering (IBR) that extends the idea of the light field but with a practical twist. It incorporates both image data and geometric informations to create the realistic rendering of the real-world scenes from any viewpoint. While the light field represents all the light rays in a space purely as a collection of captured images, it often requires thousands of viewpoints and enormous data storage to represent the complex scenes accurately. The lumigraph, introduced by the researchers at Microsoft and Catlec, overcomes these limitations by combining a coarse geometric model of the scenes, for example, a 3D mesh or the depth map, with the captured light rays. This geometric information helps to guide how light rays are sampled and reprojected, reducing the redundancy and improving the rendering quality even with the fewer input images. In simple terms, this lumigraph acts like a smart light field. It uses just enough geometric to understand where surface exists and how light interact with them. Without building a fully detailed 3D model during a rendering, the lumigraph systems reprojects the stored image based on the geometric model and then blends them to synthesize the desired new viewpoint. This approaches maintain the realism of the light field while being far more efficient in computations and storage. Examples for lumograph is: imagine capturing a statue inside a museum. Instead of photographing it from hundreds of angles, you capture it from just a few key positions. You also create a rough 3D model of the statue's shape using a depth sensors or structures from motion techniques. When you want to view the statue from a new position, the lumograph uses the geometric model to reproject and blend the available images, generating a smooth, accurate new view, complete with the natural light and texture. This technique is widely used in virtual reality tour, telepresence, movie productions, and 3D visualizations where high realism is needed by capturing the dense image data is impractical. So basically, what is this light field? In a computer vision, a light field describes the amount of light traveling in every directions to every point in a space. It is a 4D functions that represent the intensity of the light rays as they pass through the regions. Instead of just capturing the color and brightness at each pixel, like a normal camera, a light field captures both the position and the directions of each light rays. What is a concept here? A conventional camera records a 2D projections of a 3D scenes, meaning some depth information is lost. A light field cameras, however, captures that angular informations of incoming light rays using a micro lens array placed in front of the image sensors. So each pixel in the image contains multiple samples from slightly different viewpoints, allowing you to refocus the images after capturing. Estimate depth and 3D structures renders new viewpoint of the same scenes. Mathematically, a light field is represented as light of u, v, s, t, where u, v is a spatial coordinate, that is a position, and s, t is the angular coordinates, that is the directions of the light rays. So how light fields are used in a computer visions? There are many applications over that. First one is that 3D reconstructions. The light field data helps to reconstruct accurate 3D surfaces by analyzing the light rays intersections. Second one is a depth estimation. Since light fields cameras captures multiple viewpoints, they can infer scene's depth from the ray disparities. Third one is refocusing. Users can adjust the focal plane after capturing an images. That is known as a computational refocusing. Fourth one is a image-based rendering, where light fields enable the rendering of the realistic views from the mobile camera's positions. So it's used in a VR and AR, that is augmented reality. Fifth one we can say is the object recognition, where multiple viewpoints is captured by the light field, helps in recognizing the object from a different angles. Some of the real-time example like electro light fields camera, that is a consumer product. Here it captures a full light field instead of a flat 2D photos. Allows the user to refocus an image on any subjects that capture in it. Example, you take a photo of a flower and can later refocus on a background object, all from one shot. Here is a Google light field videos captured. The research project here is used to immersive VR scenes, enable smooth transition and view interpolations between the recorded viewpoints. Next is the Stanford Light Field Archive, a data set used by researchers to test the view interpolations and depth estimations algorithm. The fourth one here is a Microsoft Light Field Rendering, that is the lumograph. It is used in a 3D telepresence and image-based rendering to generate the photorealistic views without explicit geometry. And the fifth one here is the autonomous vehicles, where the light field sensors provides better depth and object shape perception for complex driving environment. In simple terms, think of the light field as capturing not just what you see, but also how you see it. So from every directions at once, it's like having a tiny camera array inside a single lens. So giving a computers the ability to see the depth, defocus and even more viewpoint after the photo is taken. So this is all about this topic. And then next we can go to the next topic. So basically the light field is about the conversions of the amount of light traveling in every direction through every point in a space. The main usage of here is augmented reality and many more in a future trends. We can move to the next topic. Lumigraph. A lumigraph is an advanced image-based rendering techniques that builds on the concept of a light field but makes it more practical for real-world applications. While a light field captures the full flow of light rays in a scene, it requires a huge numbers of images which can be impractical. The lumigraph solves this by combining a limited set of captured images with the geometric informations like a depth or a rough 3D models of the scene. To reconstruct a new viewpoints efficiently, in essence, a lumigraph stores how light interact with the surface along with some special structures of the scene. When generating a new view, it uses this geometric guidance to reproject and blend the captured images, producing the realistic renderings without needing thousands of input images. Example, imaging photographing a museum statue. So from just a few angles and creating a rough depth map of its surface, using a lumigraph, you can generate a smooth new viewpoint of the statue as it you are walking around it without missing details or distortions. So this allows the virtual tools, VR environments and movie special effects to be created efficiently and realistic. What is a key idea? A lumigraph is a smart light wave field that combines the image, data and geometry to create realistic new view of the scene efficiently, overcoming the heavy data requirement of traditional light fields. We have to talk about here is the environment meets. The environments are the technique used in image-based rendering to separate objects from their background, allowing them to be manipulated independently. Essentially, a matte is a mask that identifies which pixel belongs to the foreground objects and which belongs to the surrounding environment. By isolating these regions, we can composite the object into different scenes, handle occlusions, or apply a special effects without affecting the rest of the images. The primary purpose of the environment mattes is to preserve realism when combining the multiple images of the layers. For example, in a scene with the moving actors in front of a complex background, the matte allows to rendering the system to maintain a proper layering so that the actor correctly occults background elements or can be placed in a new virtual environment. The environments are widely used in a film productions, augmented reality, virtual reality, and interactive simulations. So, where the seamless interactions of the real and synthetic content is essential. They also help in video-based rendering by managing the occlusions over the time, ensuring that the dynamic objects appears naturally from the different viewpoints. Example, imagine filming a person standing in front of a building. Using an environment matte, the person is separated from the background. If you want to render the scene from a slightly different viewpoint or insert the person into a new virtual cityscape, the matte ensures that the person blends naturally with the new environment without leaving any artifacts or ghost images. When we talk about the VBR, the video based rendering, which extends the principles of image based rendering to dynamic scenes where objects, lighting, or the camera itself are moving. Unlike traditional IBR that relies on static images, VBR uses video sequences captured from multiple viewpoints to synthesize new views over the time. This allows for the realistic rendering of motions, depth changes, and temporal consistency, creating immersive experiences in virtual reality, telepresence, and interactive simulations. The process typically involves tracking correspondence across the video frames, estimating the depth and motion, and then reprojecting the pixels to the desired viewpoint. The advanced techniques handle occultations, moving objects, and blending between the frame to avoid the visual artifacts like ghosting or tearing. By combining the temporal informations from the video with the spatial data from multiple cameras, the VBR ensures the newly synthesized views are coherent and photorealistic. Examples: a live concert recording from multiple cameras. Using this VBR, you can generate a viewpoint as if your virtual camera is moving through the crowd or along the stages. The technique ensures that both the performance and audience appears naturally and during the occultations like a person's walking in front of the cameras and maintaining smooth motion. So this makes it the ideal for virtual reality concert like sports replays and immersive live event. What is the key idea behind this is that the video based rendering combine multiple video streams and depth information to generate new realistic viewpoints of the dynamic scenes, allowing the viewers to navigate or interact with the motion filled environment as if they were actually present. So, in this topic, basically, what is a lumograph? A lumograph is a 4D representation of a scene similar to a light field used for image based rendering, that is IBR. It captures the way light rays travels through a scene from a multiple viewpoints without explicit modeling the 3D geometry. It is introduced by the Levoy and Hanran in 1996. Unlike the conventional 3D models, a lumograph focuses on capturing the appearance from a different viewpoints rather than reconstructing the exact geometry. Mathematically, it represents the radiance along the light rays as a 4D functions. Here, UV, as I told about the spatial coherence, that is the image plane, and S, T's are the coordinate on the camera plane, which is different viewpoints. Here, the key concept here, the lumograph stores images of a scene from many camera positions during rendering. The lumograph's algorithms interpolates between the captured views to generate the novel view. It allows the realistic rendering without explicit geometry or the textures. There are many applications. First one is a 3D scene rendering. It generates the photorealistic views of a scenes as the user moves. Example, the virtual museums choose where you can move around the exhibit and see smooth transition. Second, film industry or the visual effects is used to synthesize new cameras angles from a pre-captured footages. Example, in movies, it creates a smooth bullet time effects without complex CGI modeling. Telepresence or 3D conferencing, it captures the multiple views of a speakers and interpolate the novel viewpoint for remote meetings. Scientific visualizations, the researchers can render complex structures, example, microscopic objects from captured image without building a full 3D models. So basically how it works. In a simplified workflow, I can say first is capture it. Take images from multiple cameras or the viewpoints around the scene. Second, these captured photos is then stored in a represent like each ray of a light as a 4D tuple U, V, S, T, where they interpolate like generate the novel viewpoints by combining and interpolating the rays from the nearby captured images. The last step here is that to render it, like display a smooth realistic images from a virtual camera position here. So basically the lumograph is like a similar to the light field but includes the geometrical corrections, which was developed by a Microsoft research. It also uses approximate scenes geometry for array alignment, which handles the space barely better than the light field. It incorporates the camera calibrations and depth. It also improves the rendering accuracy and sharpness. So these are the topics we have discussed here. And additional to that, the Lumigraphs blend smooth the transitionally, so the ideal for the virtual walkthrough also. So it also extends to dynamic scenes using video lumigraphs. The data captured using a multi-cameras arrays. That is one of the difference when come to the light field. It often uses a 3D teleconferencing, which represent the hybrid approaches in a IVR system. So these are the short topics we have discussed in this lumigraph. We'll move to the next topic. Environment means in a computer vision. In a computer vision, the environment refers to the physical and contextual condition in which visual data is captured. Unlike humans, men can adapt their perceptions to varying light, weather, and surroundings. Computer vision systems are highly sensitive to environmental changes. These systems rely on images or video to detect, recognize, and track objects. The variation in the light conditions, like bright sunlight, low light, shadows, everything's like a weather effect, like rain, fog, snow. The background complexity and the object accumulations can significantly reduce accuracy. For instance, autonomous vehicles may misinterpret lane marking or fail to detect pedestrians under poor visibility, leading to safety risk. Similarly, security cameras may struggle to recognize faces or movement during the night time or in environments with the glare or reflections. To address these challenges, researchers and engineers employ several strategies. First one is data augmentations. By artificially modifying the training images, changing brightness, or any adding noises like rotating or flipping, models learn to generalize across different environmental conditions. The multi-sensor fusion, which combines the visual input with other sensors like lidar, infrared, or radar, improves the reliability in a low visibility or harsh environmental. Third one is the domain adaptations. Here, the advanced deep learning methods allow the models to train in one environmental, example sunny day, to adapt to another, example rainy or foggy conditions, without retraining from the scratch. So fourth one is the image processing, or we can call as a image pre-processing. It is a techniques like histogram equalizations, noise reductions, and contrast enhancement helps to standardize image from analysis. The environment also influences data design, which is critical for training the robust model, like large diverse data sets that includes images captured under different lighting angles and weather conditions that are essential for building real world ready computer vision system. So to conclude this, I can say ignoring the environmental factors in a computer visions can lead to a poor performance, unreliable predictions, and even safety hazards. So recognizing that environmental matters, so ensure the computer vision models are robust, adaptable, and capable of performing reliably in the real world. For applications ranging from autonomous vehicles to the medical imaging and robotics, understanding and integrating environmental context is a crucial as algorithms themselves. There are many applications and environmental considerations. The importance of environmental in computer visions becomes even clearer when we look at real world applications. The autonomous vehicles, for instance, relies on cameras and sensor to detect the lanes, traffic signs, pedestrians, and obstacles. The environmental factors such as rain, fog, snow, or even a strong sunlight can create a reflections, glare, or blood images, potentially leading to the misinterpretations by the systems. The engineer addressed this by integrating multi-sensor fusions, combining the visual cameras with LiDAR and radar as well as the infrared sensors. So the vehicle can perceive its surroundings accurately under all conditions. In surveillance systems, lighting changes from day to night or shadows cast by building can confuse the motion reductions and facial recognitions algorithm. To improve the reliability, developers often use infrared cameras or thermal imaging to detect the objects in a low light or nighttime conditions. Similarly, in robotics, environmental factors such as cluttered spaces, moving obstacles, or inconsistent lighting can affect the object directions and navigations. So here, the robots are trained with a simulated environment that mimic the real world variations, allowing them to adapt the more effectively. So, what are the challenges we are going to face it? Despite the technological advances, environmental variabilities remains a key challenge in a computer visions, like a model trained on a controlled or a ideal dataset may perform poorly in the real world due to differences in a weather, lightning, or backgrounds, a problem known as a domain shift. Additionally, extremes environmental such as underwater explorations, outer space, or disaster zones introduce unpredictable conditions that standard model struggles to handle. Future actions. So, future research in computer visions focuses on making model and environment aware and robust to change. So, the techniques like unsupervised domain adaptations or self-supervised learning and synthetic data generations helps the systems to learn from diverse conditions without needing exhaustive real-world data. The advanced sensor technologies and AI algorithms that can dynamically adjust to the environmental conditions are also being developed. So, to conclude this, in a computer vision, the environment truly matters because it directly influences the perceptions, interperceptions, and the decision making by machines or any built-in robots. It is adaptable systems require understanding the challenges posed by real world conditions and designing the solution that account for variability. From autonomous vehicles to the robotics and medical imaging, considering the environmental factors ensures the safety, reliability, and effectiveness, proving that real intelligence is not just about seeing, but also about understanding the context in which we see. So basically, in these topics, we have discussed about the how transparency and reflections properties of the objects basically, and separate objects from the background with the environmental context, and also extends the traditional alpha method. So here it captures how light interact with the environment. It's also used in a realistic compositions as well as in a rendering methods. It enables the objects to reflect and refract the background. Here, it is a three-layer representations. So basically, if you are given a pictures in a 2D graph, there are three layers of the perceptions or the representations of that particular 2D graph. First one is the foreground that we see in the frontal view, and next second one is the background that we see in the back view of behind the front ground. Next is the reflections. So how the lighting plays a vital role. For example, if lighting is from the side, so how that is going to affect these two foregrounds as well as the backgrounds. So this also plays a major role when come to the layer representation of that. Next one is a key for augmented reality applications, and some of the points we have discussed on that. And it's also repairs acute lightning interactions, which requires environmental sampling like light probes. So here it enables the object insertions into a real scenes. So the real time meets generate via depth cameras. So when we are going to capture something, it should be in a more detailed format. It might be from starting from a picture to anything. So here the real time meets generate via depth camera. That's plays rewards. It also improves the photorealistic object blending, and it handles the transparency and glossy matters. So it supports real lightings under new conditions or any conditions over that. It's also used in our films like VFX, right? Blends. It's combined computer visions with image synthesis, and it requires a precise segments and color modeling. So these are the topics we have discussed in this. We are moving to the next topic. Video based rendering, that is VBR. The video based rendering is an advanced technique in a computer vision and computer graphics that focuses on creating new views or scenes from existing video footages rather than relying entirely on a 3D models or a synthetic graphics. In simple terms, it allows the computers to generate realistic visuals from a real world videos using captured data from cameras to synthesize new perspectives, motions, or effects. Unlike traditional 3D rendering, which builds scenes using the geometric models, textures, and lighting equations, video based rendering uses real video frames as a main source of information. The system analyzes multiple video streams of the same scenes, that is often taken from different camera angles, extracts depth and motion informations, and then reconstruct or re-renders the scene from a new viewpoint. This process helps to produce extremely realistic results since the textures and the lighting comes from the real world footage. So basically how it works, there are 5 steps over that. The first one is the video capture. So the multiple cameras records the scene from a different viewpoint or angles. Second one is the calibrations and alignment. The systems calculate the camera positions, orientations, and synchronizations across the frames. So here, the depth estimation is that it's used in the stereo visions or the structure from a motion techniques. The depth or a 3D geometry in estimated from the videos. The fourth one is a image based rendering. The system reprojects the pixels from the existing frames to create the new views, blending them smoothly to fill in missing areas. So the post pre-processing or the processing is a techniques like optical flow, interpolations, and neural renderings refines the final output for realism and consistency. There are many applications. Some of them are VR AR, that is a virtual reality and augmented reality, is used to create immersive environmental from the real video scenes. Or second, we can say like a movie productions and any special effects. It enables the realistic scenes reconstructions and view synthesis without expensive CGI modeling. So the next one you can say about the autonomous vehicles, where it helps to simulate the realistic environments for training the vision systems, as well as in the sports broadcasting. It allows a dynamic replay and free viewpoint videos where viewers can watch the game from any angle. The last example of the application I can say it's a medical imaging and the telepresence. It enables a realistic visual reconstruction in a remote diagnostics or any 3D visualizations. There are many challenges. Some of them is that it's occlusion handling. Here it's managing the hidden areas that are not visible in a captured views, and lightning variations where it is differences in the brightness and shadows between the video sources can cause inconsistency. Third one is a computational cost where the rendering from a multiple video sources and reconstructing a new view requires high processing power. Next one is a depth estimations areas where it is inaccurate geometric lead to distortions or visual artifacts. Now modern advances, recent development in AI and deep learning have significantly improved the video based rendering like neural radiance field like NUF and neural rendering techniques can now reconstruct the photorealistic 3D scenes from just a few video frames. So these methods use neural network to models how light interact with surfaces, making view synthesis more accurate and efficient. So to conclude this, like a summary, the video based rendering bridges the gap between the real world footages and synthetic graphics. So it enables the machines and creators to reproduce reality with the high fidelity using a video data as a foundations. Whether for virtual reality, film productions, or autonomous navigations, this technique shows how visual computing is evolving towards more immersive, realistic, and environmental aware experiences. As research continues, the VBR will play a major role in shaping the future of computer vision, simulations, and digital content creations. When talking about the advanced techniques in video based rendering, as technologies progress, traditional video based rendering has evolved into a AI driven and neural based rendering, which combines the principles of computer vision, machine learning, and a computer graphics. These new techniques make rendering more accurate, realistic, and computational efficient. When we discuss about the nerve, that is a neural radiance field, the nerve is one of the most revolutionary technique in recent years. It uses the deep neural networks to represent a 3D scenes as a continuous volumetric functions, predicting the color and density for every 3D point in a space. By feeding the video's frames from a different viewpoint into the models, the nerves can synthesize the novel views that were never captured by a real cameras, achieving stunning realism. Second one is a view interpolations and frame synthesis. The algorithms use optical flow and depth estimation to interpolate the frames between the existing videos, creating smooth transitions or completely new perspectives. So this is widely used in slow motion videos, generate and view free viewpoint video experiences. So image based and hybrid rendering. Here some systems combine the image based rendering, that is which is uses real pixel data, with geometric based rendering, which uses a 3D model to maintain both the realisms and spatial accuracy. This hybrid approaches is popular in a film productions and mixed reality environment. Next one is a deep video implanting. When certain part of a scene are missing or occluded, the deep implanting networks can fill in missing informations by learning the pattern from the surrounding frames. This enhances the continuity and completeness of the rendered video. There are many roles in environment, particularly in a VBR. Just like a computer vision, environment factors such as lighting, shadows, reflections, weather conditions, and camera motions plays a huge role in the quality of the video-based rendering. The first one is a lighting inconsistency, like between the different cameras angles can cause a visual artifacts when blending the frames. Second one I can say is a dynamic environment, like moving clouds, water reflections, or flickering light add complexity because the scenes constantly changes. Next one is a camera instability or motion blur can make the depth estimations and frame alignment more challenging. To counter these issues, modern systems apply environment aware algorithms that automatically detect and adapt to such variations. For example, illuminations normalizations and shadow removal techniques ensure consistent lighting, while motion stabilizations and scene segmentations help to maintain the accuracy even in a dynamic or the outdoor environment. There are many applications in the real world scenarios. First one is a virtual tourisms. User can explore the famous landmarks through the reconstructed 3D video environments as it they were physically present. Next one is a cinematic effect, where the film studios uses VBR to create a complex camera movement in a scenes that were filmed with a limited viewpoints. Next one is a sports and broadcasting with a multi-camera setups allows the audience to rewind and view plays from any angles direct application of the VBR. There are autonomous systems where the robots and self-driving cars uses this VBR to build a 3D environmental map from a 2D camera feed for navigations and safety. Next one is educations and training, which simulates the environmental rendered from the real video data are used for virtual classrooms, flight simulators, and surgery trainings. Some of the future scope I can say that the future of the VBR lies in the combining of the combinations of the AI, physics-based simulations, and real-time rendering with faster GPU and advanced neural models. The VBR will soon allow interactive experiences like live holographic meeting or AI driven video scenes reconstructions. The integrations with Gen AI can also enhance the realisms, for example, generating the unseen part of a scene or adjusting the environmental conditions like changing to day to night, clear sky to rain, etc. in a real time. Moreover, sustainability is becoming a consideration. Instead of manually recreating the 3D models for virtual world, VBRs can directly use the real world video data, saving both the times and resources in industries like entertainment, civilizations, as well as the digital preservations. To conclude this, in essence, the VBR is reshaping how we perceive, the recreate, and interact with the visual reality. By blending the computer vision graphics and AI, it enables the transformations of ordinary videos into an immersive, interactive, and intelligent 3D experiences. So, as the research continues to improve the environmental adaptability and computational efficiency, VBR stands at the frontier of the next generations of a virtual content creation, simulation, and machine perception, proving that the bridge between the real and the content creations, simulations, and a machine perception. Proving that the bridge between the real and the digital world is now built with pixels, light, and learning. So, these are the topics we have covered. We are moving to the next topic now. Introductions to recognition. Recognition in a computer vision and artificial intelligence refers to the process by which a system identifies and classifies the object, patterns, or features within the images or videos. In simple terms, it enables the machines to see and understand what they are looking at, just like a humans do. Recognition is a fundamental goal of a computer vision. It allows the computers to interpret visual data and make meaningful decisions based on it. Recognitions can occur at a different level. At the most basic level, a system may recognize the shapes, edges, or colors in an image. At a higher level, it can identify specific objects such as faces, vehicles, animals, or any handwritten text. So, the modern recognition systems can even understand the complex scenes, detecting multiple objects and their relationships. For example, recognizing that a person is driving a car or holding a phone. These are some of the examples. So the process involved generally have some four steps. First one is a image acquisitions, where it captures the input data through a camera or a sensors. Second, it pre-processing by enhancing the image quality or removing the noise and adjusting the lighting or the contrast. Third one is a feature extractions, where it identifies the important characteristics like edges, textures, patterns, etc. that help in recognitions. So the fourth one is the classifications or matching, using algorithms or trained models to compare the feature and assign the labels examples cat, tree as well as car. There are many types of recognitions includes object recognitions, face recognitions, gesture, speech recognitions as well as a scene recognition. With the rise of the machine learning and deep learning, especially in a CNN, that is a convolutional neural networks, recognition's accuracy has improved dramatically, enabling the real world applications like autonomous vehicles, surveillance systems, medical image analysis, and augmented reality. To summarize this, recognition is a core capability that gives the intelligence to visual systems. It transforms the raw image data into a understanding or the bridging the gap between the human visions and a machine perception. As technologies continue to advance, recognition systems are becoming fast, more accurate, and increasingly capable of the interpreting the world around us. There are many types of recognitions as we discussed before. We'll see some of them in a more detailed format. So recognitions in a computer visions can be classified in many different based upon the objects or the pattern being identified. The first one is the object recognitions. This is the most common form of recognitions. It involves identifying the specific objects within an image or videos such as cars, chair, animal or tools. For example, in an autonomous vehicles, object recognitions helps to detect the pedestrians, vehicles and the traffic signs to make driving decision. Second one is the face recognitions. So the face recognitions identifies and verifies human faces from images or videos. It is widely used in security system, smartphones and attendance monitoring. The process includes the face directions, feature extractions like a distance between the eyes, shapes of the nose or a jawline, and matching against the stored database. Third one is a scene recognitions. Here the scene recognitions goes beyond a single object to understand the overall environment. It allows the systems to identify contents like beach, city street, office or kitchen. This helps in autonomous navigations, photo organizations and AR/VR application. Next one is the gesture recognitions. Here gesture recognitions interrupts human movements or a body postures to enable interactions between a humans and a machines. It is used in gaming, robotics and touchless controls interfaces. Next one is a speech and text recognitions. Although not purely visual, speech and optical characters recognition, that is OCR, are also types of recognitions where machines interrupt spoken words or printed the text, converting them into a digital data. Next, we have to talk about the techniques used in recognitions. Early recognition systems relied on manual feature extractions, that is, engineering design specific rules or filters to identify the patterns. However, with the advancement of artificial intelligence, especially deep learning, recognition has become more data driven. First one is a feature based method. These methods use handcrafted features like shift, scale invariant features transforms. This is one of the algorithm. Same like there are many algorithms like surf, speeded up the robust feature, or hog, histograms of oriented gradient to detect and describe the pattern. Second one is a machine learning approaches where the algorithms such as SVM, support vector machines, or K nearest neighbor KNN are used to classify the extracted features into a predefined categories. Third one is the deep learning methods where the modern systems use CNN with automatically learn hierarchical features from the raw images data. So here the CNS has revolutionized recognitions, accuracy, and are now the foundations for models like ResNet, BGG, and YOLO. It is you only look once. The last I can say is the hybrid and the context aware models, where the newer approaches combines multiple techniques and incorporates the environmental or contextual understanding like lightning, motions, or any spatial relations to improve the recognitions in the real world scenarios. There are many challenges here. Despite the great progress, recognition systems face several challenges like lightning and weather variations. So, the changes in brightness or any environmental conditions can affect the accuracy. Here, the oscillations when objects are partially hidden, recognitions become difficult. Pose and orientations, objects or faces viewed from unusual angles may not match standard training data. Next one is the data quality. Here the low resolutions or a noisy images reduce the model performance. The last I can say is the bias and fairness. Datasets that lack diversity can cause biased or unfair recognitions result. The researchers are working to overcome these challenges through data augmentations, transfer learning, domain adaptations, and multimodal systems that combines the visual, auditory, and spatial information. There are many applications of recognitions. First one is a recognitions technologies has become deeply integrated into everyday life and industry. First one is autonomous vehicles where for directing the lanes, sign pedestrians and other vehicles is being used. And in a security and surveillance, face and object recognitions helps in threat detections and access control. When come to the healthcare field, medical image recognitions like it's in a diagnosing the disease from the X-rays, CT scans, or even in MRI images. Next, coming about the smart devices. Smartphones use recognitions for unlocking the systems, tagging photos, and enable the AR features. Next is the industrial automations, where robots use recognitions to identify and handle the object in a manufacturing. And talk about the HCI, that human computer interactions, gesture recognitions in a gaming and virtual environment plays a vital role. To conclude this, recognition is a foundation of intelligent visual system. It allows the machines not only to observe but to understand and interpret the visual informations. With the growth of deep learning, big data, and computational power, recognition systems have reached human level performance in many domains. However, achieving the reliable recognitions across varying environment and conditions remains an ongoing challenge. As technology evolves, recognitions will continue to bridge the gap between human perceptions and artificial intelligence, shaping the future of automation, safety, and intelligent decision making. So that's all. These are the topics we have discussed in this. We'll move to the next topic. Object directions. Object detection is one of the most important tasks in computer vision that involves both identifying, that is recognizing, and locating the localizations object within an image or videos. While image classifications only tells what object is present, object detection tells what and where by drawing the boundaries boxes around detected object. Examples: if an image contains a car, pedestrians, and a traffic light, an object detections model will identify each object like a car, person, traffic light. So these are the small things or the object that is detected using this object detection software. Here, draw a bounding box around each one, which assigns a confidence scores. Example, like car is 98%. Like that, it will be assigning to that. So, how this work? First one is that there are many steps, but I'll conclude it with the 5 steps. First one, it is image input or video frame. The image is provided to the models for analysis. Second one is a feature extraction. Here the model extracts visual patterns like edges, textures, color, shape, or even using a CNN model like convolution neural network to this. The region proposer or sliding window, the system identifies a candidate region that might contains object. Fourth one is the classifications and localization. Each region is classified, what object it is, and localized bounding box coordinate are predictors. Next one is the post processing. Non-maximum suppressions NMS is applied to remove the duplicate or overlapping boxes and keep only the most confident detection. The popular object detection technique I can say is that first one is a traditional method, that is a pre-deep learning era, where before deep learning object detections relies on handcrafted features like air gaskets. It used in early phase detection systems like OpenCV phase detector in a Python library. Next is a HOG, that is a histograms of oriented gradient, plus SVM support vector missions used to detect the pedestrians and a vehicle. And the third one is a sliding windows technique, where it scans the image in a small sections, classifying each patches. So it's slow but foundational. And the second step or second level of detection I can say is a deep learning based method, that is we call as a modern approaches. Here the hard CNN, that is the regional based CNN, come into the picture, which was proposed by the Ross Kirschik in 2014, which generate the region proposal, then classify each with a CNN. Accurate but slow, but because it processes each region separately. To come with a fast RCNN and faster RCNN, it improved the versions of RCNN, faster it, and it was introduced by the Region Proposal Network RPN to speed up the directions very accurately and widely used in a research area. Next one is a YOLO, you only look once. Real-time object detection systems, which divides the image into grids and predicts bounding boxes and classes simultaneously. Like variants like YOLO V3, YOLO V5, YOLO V7, YOLO V8, and so on. which are widely used in a practical application. These STST, that is a single shot multi box detectors, similar to YOLO but use multiple features maps for detecting objects at a different scales. So it balances the speeds and accuracy. Next one is a vision transformers. We call this as a VIT, where the and as well as a DETR, which are newer architectures using the transformer models from NLP, where the detections transformers learns object detections and end to end without regional proposal. To evaluate these matrices or to measure the detections performance, we can use precision for how many predicted objects are correct, and we can use recall, like how many actual objects are detected, as well as HIOU, the intersections over the union, which measures how well the predicted boxes overlap with the actual ones. Next one is a map, that is a mean average precision, where standard benchmarks combining precisions and recall over the multiple classes. Even though there are many techniques involved in this, like a traditional and modern approaches, there are many challenges to detect in object detections. First one, as I said, is the occlusions, where an object partially hidden. Example, a person behind a car, as well as a scale variations, like same object appears larger or smaller depending on the distances. Third one is the lighting conditions, where poor or uneven lighting reduces the accuracy. There are like real-time recruitment, like process speeding is critical for applications like autonomous driving and cluttered background, which have multiple overlapping objects, which increase the complexity. But even though there are many applications for object reactions, for detect the pedestrians, vehicles, like road signs in real times, and to identify the suspicious activity or unauthorized access or intrusions or even a specific individual for that. It's also work on a track products on shelves or monitor checkout counters automatically. So here it detected tumors or anomalies or organ in X-rays or even in MRI scans. So these are some of the applications. When come to the agriculture, it identifies the crop diseases or count fruit for yield estimations. In smartphones, we can say real-time face filters, augmented realities, and barcode scanning. So there are many applications for this. To conclude that, I can say the object detections has evolved from a single pattern matching technique to a powerful deep learning models capable of real-time accurate detections of a multiple objects. With advancement like YOLO V8 and data detections, systems are now faster, smarter, and more adaptable, enabling a wide range of the real world AI driven applications. So, in this topic, we have discussed about how it locates and classifies objects in an image, or the output boundings boxes with the class labels. So, it combines the localizations and classification tool. That is what the main idea here. The feature extractions like ResNet, BGG, they'll be used for that. Algorithm like RCNN, fast RCNN, YOLO or SST is discussed, and also about the anchor boxes used in the regional proposals with multi-scale reactions handles different object sizes over that. It requires annotated boundaries that boxes data sets. So it requires like evaluating matrices. We use recall, precisions, etc. It used, and some of the applications like it's used in the surveillance, autonomous driving, retails, and medical imaging, so on. It is a temporal directions extended to the video streams, but we have to find the false positive to minimize the contextual filtering, where the object detections forms a basis for instant recognitions. The pre-processing includes normalizations and resizing. The post-processing merges overlapping directions which integrate with the tracking for motion-aware systems, advanced methods used in the data. So the key steps towards a visual scenes understand. So these are the topics we have discussed so far about this. There are many applications using these object directions and many techniques also, starting from base the traditional one to the advanced the modern one. So we can move to the next topic. Similar to object recognitions, there is a face recognitions. So face recognition is a subfield of a computer vision and a biometric identifications that focuses on identifying or verifying a person identity using their facial features. It allows the computer to see and recognize human faces just like humans do. But through mathematical and computational techniques, face recognition systems are now widely used in mobile phones, surveillance, border security, attendance systems, and social media platforms for tagging and authentications. Example: when you unlock your phone using a Face ID, the system scans your face, extracts unique pattern and matches them with the stored face data to verify your identity. The difference between a face directions and face recognition is that face directions find and locate the face in an image, which tells where a face is. Face recognition is identify whose face it is and tells who the person is. For example, a system may first detect that there are three faces in an image, that is called detection, and then recognize them as a person A, person B, as well as person C. So this is what is called as the recognitions. So how this face recognitions works? The face recognitions process typically follows these main steps like face directions. The systems first detect the presence and the position of the face in an image or the video. Common method, that is basically like they can use many algorithms like air gaskets. So this is a traditional open CV methods. Next one is the OG plus SVM, that is a histograms of orientations gradient plus the support vector machines. Third one is the deep learning interactions like MTCNN, SST or any retinal faces. Second one is that after detecting, it will do face alignment where the detector face is aligned, rotate or scaled like a edit process. So that the key features like key eyes, nose and mouth are positioned consistently. So this helps to ensure that all faces are compared in the same orientations. Third one is the feature extraction. The system extracts a numerical representations called embedding of a unique facial feature such as eye distance, nose shape, jawline, cheekbone structure, etc. These deep learning models use CNN, that is a convolutional neural network, to automatically learn these discriminator features. Fourth one is a matching, that is the last steps. We call it as a feature comparison. Here, the extracted features are compared to a database of a known faces using a distance metric. Example, Euclidean or a cosine distance. If the similarity score is above a threshold, the face is recognized as a match. If it is not, it will be rejected. Some of the popular face recognition algorithms and models, it's eigenface, that is PCA, principal component analysis, where one of the earliest method, it reduces the image dimensions while keeping the essential face informations. So it works well for a small data sets but falls under the varying lighting or pose. So that is one of the drawback in this. Next one is LDA, linear discriminated analysis. We call as a Fisher faces, which improves over the PCA by maximizing the difference between the individuals while minimizing the variation within the same persons. There is another algorithm called LBPH, where the local binary patterns histograms plays a vital role, which extract the local textures pattern from an image, works well with grayscale images and small data sets. Fourth one, I can say it's a deep learning based model. This is a modern approaches in this algorithm. First one is a deep face. This is used in a Facebook, the first large scale deep learning models for face recognitions. Next one is a FaceNet. This was used by Google, where the map to each face to a 128 dimensional embedding vectors for higher accuracy. Next one is a VGG phase, the VGG phase as well as VGG phase 2. It was used by Oxford, where deep CNN model trained on a millions of faces. Next one is a deep face recognitions. It's a popular open source implementations using deep learning embeddings. To evaluate these matrices, you can use recognitions accuracy RA, like percentage of correctly recognized faces, and FAR, false acceptance rate, like probability that an unauthorized person is incorrectly accepted. Next, FRR, false rejection rate, where the probability that an authorized person is incorrectly rejected. Next one is ROC curve as well as AUC, where it shows the performance trade-offs between a FAR and FRR. There are many challenges in face recognitions. First one is the lightning variations, where the shadows and the bright light affect the feature extractions. And second one is the pose variations, where the faces turn sideways or partially covered are hard to detect. Third one is the aging, where faces change over the time due to age, facial hair or makeup. Fourth one is occlusions, where the masks, sunglasses or scarves can hide key facial parts. Fifth one is a privacy concern, where the facial data is sensitive and raises ethical and the legal issues. There are many applications of face recognitions. First one is that it will identify the suspect, like track the movement in a public space. This is for security and surveillance. Next one is that face unlock, which is used in smartphones and any biometric authentications like Apple Face ID, Android Face Unlock. So this and all be one of the applications. Next one is attendance systems, where it is used in schools, office and organizations for contactless attendance or counting the attendance entry, etc. Next one is a face-based identity verifications for secure transactions like banking or a payment verifications. Like auto tagging friends in a photos in any social media platforms like Instagram, Facebook, etc. It also used in healthcare for patient identifications and monitoring in hospitals. Next one, it is used in a law enforcement agencies, used in criminal identifications and investigations, especially when coming to the forensics department. To conclude this, face recognitions as revolutionize the way machines identify the individuals, making interactions more seamless, secure, and personalized. From early mathematical models like eigenfaces to advanced deep learning architectures like FaceNet and VGG face, accuracy and reliability have improved dramatically. However, as the technology grows, it's equally important to ensure the data privacy, fairness, and ethical use of the maintain trust and balance between the innovations and as well as responsibility. So in this topics we have covered how this face recognition identifies the individual based upon the facial features, like the to detect, first it will detect alignment encoded as well as it will be entered up with the matching. So it extracts the facial landmarks and embodied basically. And also we have discussed about some of the traditional methods and model approaches in this, and how it works under varying illuminations and positions. And we also discuss about the CNN based architectures where different companies use like Google, Oxford uses a different algorithm for this facial recognitions. It is also privacy preserved recognitions. It's now an emerging techniques or the trend over that, as well as the Edge AI supports the real-time facial verifications, where the major advancement is a biometric systems or any authentication systems. So these are the topics we have discussed in this. We'll move to the next topic. Instance recognition in a computer visions refer to the task of identifying a specific object instance, not just its category within an image or videos. While object recognitions or image classifications recognize the category of an object, example, this is a car. The instant recognitions goes one step further and identify the exact instance. That is, this is maybe a particular person A's red car BMW. Like that, it will specify the persons as well as whose car it is and more detail to that particular detected images. Example, if you have three different cups, object recognition will label all of them as a cups, but instance recognitions will tell you which specific cup it is based on the shapes, design, color, or the texture differences. So this is how we are going to differentiate between that. Let's see how this work. First one is the data collections. A data set of a specific object instance is collected. Example, different bottles, specific cars, or product items. Each image is labeled according to its instance, not just its class. So the feature extraction here, the system extracts the detailed visual descriptions that captures the unique pattern, texture, shapes and color detailed. Earlier, handcrafted features like shift, surf and orb were used. Now, deep learning models automatically learn discriminative embedding using CNN or transformers. Third one is the representations or matching, and as well as matching because each instant is represented as a feature vectors or embodied in a high dimensional space. Next one is that during the recognitions, input images embedding is compared with those in the database using a similarity matrices. Example, cosine similarities or Euclidean distance. Next one is the classifications or retrieval. The most similar stored instant is selected as a recognized match. Alternatively, the top end similar instances are retrieved as in image retrieval systems. Some of the traditional technique involved is that before deep learning, instance recognitions relied on a local features descriptors such as shift, scale invariant feature transform, which extracts a key point and descriptors that remain stables under scale and rotation changes. Second one is a surf, which speeded up the robust features, a faster variant of a shift used in a real-time system. Third one is a orb, where the oriented fast and rotated brief will be working on, where the efficiency for the model or the mobile embedded applications will be useful. Fourth, I can say, is a bag of visual words like bow. It represents the images as distributions over the visual words to derived from the feature descriptions. So these techniques worked well for a small or controlled data set but struggled with the large scales or a real world versatility varieties. So, where the deep learning based approaches came into the pictures. So, with this deep learning, the instance recognitions become more powerful and scalable. Like CNN model, this is based on the embedding models where the networks like ResNet, VGG, and Inceptions extracts the deep features that captures the subtle differences between the instances. Second one is a SIMS network where it learned to compare two images and determine if they belong to the same instance. It's also used in a phase verifications and product matching task. Third one is a FaceNet where it learns embedding where images of the same instance are closer together and different instances are farther apart. Fourth one is a VIT Dino and Clip where it provides a context aware and alternative based embedding that performs well in a fine grained and instance levels recognition systems. To evaluate these matrices, precision as well as recall is used, like how well the systems retrieves correct instances. Top K accuracy we can use to whether the corrected instance appearance in the top K predictions or not. Third one is the mean average precisions, that is we call as a map, where the common matrices for large scale retrieval tasks will be using on. Fourth one is the embedding distance matrices to evaluate the similarity between the image representation. But there are many challenges in instance recognitions. First one is the intra-class variations. The same instance may appear differently due to lighting, angle or occultations. As well as in inter-class similarities, different instances may look very similar. Example, two identical phones. Scalability, like a large data sets with thousands of instances increase computational load, as well as some instances have more training images than others. To talk about the real-time constraint, high-speed matching is required in applications like robotics or any augmented reality. There are many applications of instance recognitions like retail e-commerce where the product will be identified for inventory tracking or visual search. Example, search by image features on Amazon. So all be used on that. Next one, to recognize a specific vehicle, road signs or any landmarks. It also works on the enabling the robots to identify and interact with a specific object in a cluttered environment. In museums and any hard digitalizations, recognition specific artworks or artifacts for cataloging and study will be used on. Recognizing a particular persons across different cameras or times that is used in the surveillance and across the systems. Detecting and anchoring virtual objects on a specific real world instances used in particular with the augmented reality. To conclude this, instance recognitions represent a deeper level of understanding in a computer vision, moving from the classifying the object types to identify the individual's objects uniquely. With the rise of deep neural network, especially Siamese and transformers based models, systems today can distinguish even minute visual differences between instances. Its ability to connect perceptions with identify makes it a core technology in a modern applications ranging from the retail stage to the autonomous systems and as well as the biometric verifications. So basically in this topic we have discussed about recognition specific objects instance and not just a category, and some of the example to identify a specific car models, and it requires a detailed feature representations like sift surf or used as a traditional methods. when deep learning come into the picture, the CNN features outperforms the handcrafted descriptors. It works well with the fine-grained data sets. It's also used in product recognitions and visual searches, where it handles a viewpoint and illumination changes. So it relies on a key point matchings or any feature similarities, where these sleep metric learnings used for embedding the space. It is also used in AR object placement, where aids in a forensics and museum aircraft recognitions, which requires a high intra-class discriminating. Like multimodal fusions improves the robustness, datasets and notions more specific than the category recognitions. It performs depends on the visual uniqueness used in inventory, automations, and e-commerce. It also bridges the perceptions and identifications. So these are the topics we have covered under this. Basically, instance recognitions is different from the object detections or any other recognitions, because when some other systems going to detect something, it will only say the general view about that. But when come to the instance recognition, it give you the view perceptions or the deep perceptions about the each object that is detected. So we'll move to the next topic. Category recognitions. So, category recognitions is a computer visions refers to the process of identifying and what category or a class an object belongs to or within an images or video. In simple terms, it answers the questions what type of object it is, like not which specific object. Example, if you show a model image of a car, dogs, and a car, it is correctly labeled them as a car, dog, cat, whatever it is. Performance a category recognitions. So that the goal of the category recognition is to assign each images or the object in an images to predict or predefine the category labels such as a person, vehicle, flower, building, etc. So how does this work? First one is a image acquisition. An image is captured by a camera or obtained from the dataset. First, second one is a pre-processing these acquired data. The image is resized, normalized, or augmented like a rotation, flip, brightness, and change to make it consistent for the model. Third one is a feature extraction. The systems extracts visual patterns such as edges, textures, colors, and shape using either traditional or deep learning method. Fourth one is the feature representations. Here, the systems extract visual patterns such as edges, texture, and shapes using either traditional or a deep learning methods. Basically, in this feature representation, it's converted into a numerical representations like vectors for classifications. In classification, a machine learning or a deep learning models is trained to map these features vectors to specific category. There are many traditional techniques before deep learning. So there are like categorizing the recognizer using the handcrafted features and classical machine learning algorithms like SIFT, scale invariant feature transforms, which captures local key points and patterns. Next one is OG, histograms of oriented gradient, which represent the shapes and edge informations. Third one is SURF, which speeded up the robust features faster alternative to SIFT. Fourth one is a bag of visual world, that is BOW, where it converts the image feature into a word like cluster classifiers. Classifiers like SVM, support vectors, machines, K nearest neighbors, random forest. So these methods works well for simple low resolution images, but were limited by their inability to handle large variation in lighting, pose, as well as or background. When come to the advanced things or deep learning for category recognitions, the evaluations of a category recognitions begins with a CNN basic convolutional neural network, which automatically learn hierarchical feature from the images. The common CNN architecture we have to mention here is AlexaNet from 2012. So first CNN is to win with ImageNet challenged, like showing deep learning potential, and VGGNet is deeper network with a small filter for a better representations. ResNets introduce skip connections to handle very deep networks. Inceptions of the Google net use multiple filter size in a parallel. Like that, efficient net scales depth, width, and resolution efficient. Vision transformation VIT uses self attention instead of convolution for feature learning. These models are trained on a large dataset like ImageNet, which converts over thousands category and millions of labeled images. To evaluate these matrices, you can use many matrices here. First one is accuracy, the percentage of the correctly predicted category. Next one is the top one accuracy, where whether the top predicted is correct. Next is top 5, whether the corrected labels among the top 5 like a predictions, which is used in ImageNet. Fourth is a precision's recall F1 score. You can use any of this for categorizing the wise performance evaluations. And the last matrices you can use here is a confusion matrix to visualize how often each category is misclassified. So still there are some challenges we facing in a category recognitions. They are the intra-class variations. Same category appears differently. Example, different dog breeds. Interclass similarities. Different categories but not similar. Example, wolf versus husky. Third one is lightning force accumulations. Affects the features visibility. Background cluster, where the non-relevant details may confuse the model. Next one is the data imbalance, where some categories have fewer samples than the others. There are some applications for that. First one is the category in the photos, like vehicles, food, etc. It's used for the image classifications. Second one is that identify the inappropriate or restricted content online, like filtering process in our websites or anything. Next one is that to classify the disease, like sample tumor versus non-tumor in a medical imaging. Next, we can work on the details on any e-commerce to classify the product category for a better search and recommendations. And when coming to the autonomous vehicle, it will recognize a category like a pedestrians, vehicles, and a traffic signals. In agriculture point of view, it will identify the plant species, crops, disease categories. It will also classify the land types like forest, water, urban, everything. The environmental monitorings. So to conclude with this, the category recognition is a foundational task in computer visions which serves as a building block for more advanced recognition systems like object deductions, instance recognitions, and scene understanding with the advancement of a deep learning architectures and massive data sets and machines are now capable of recognizing thousands of categories with human level accuracy. It remains one of the most important and widely used techniques across domain from autonomous system to healthcare and digital content analysis. So these are topics we have covered in this. We can move to the next topic. Context and scene understanding. Scene understanding in a computer visions refer to the process of interpreting an entire scene in an image or videos rather than just directing the individual objects. It involves recognizing what objects are present and the relationship, spatial layout, and the overall environment. Context understandings refer to the ability to infer the meaning from the surroundings, such as predicting likely object positions, interactions, or activities based on the scenes. Together, they help the machines not only see what is there but also understand how things related to each other. Example, in a street scene understanding recognitions, car, pedestrians, buildings, and traffic light. Context understandings predicts that pedestrians are likely to be on sidewalks and cars will follow the lane. Importance of scene and context understanding is that it provides high level reasoning about environment. It also enables autonomous systems like robots car to make informed decisions. So it improves accuracy in recognition tasks by considering the surroundings, objects, and scene context. Essential for human like perceptions, allowing the machine to anticipate the action, interactions, or events. So, what is the key components in this? First one is a scene classification. To categorize the entire images into a scene like type, for example, beach, city, office, and also helps to provide the context for objects recognition task. Example, the dataset like places 365 sun database. Next is the object recognition with scene. So directing the objects in the scenes, individual their classes, instance, and the positions, it will understand objects co-occurrence, helps to improve the recognition accuracy. Example, boats are often in the water scenes. The spatial relationships determine the geometric and topological relationship between an object. Example, a couple is on a table, person is sitting on the chair. The contextual reasoning here is uses the surroundings environment to predict or redefine the object recognitions. Example, a small object in a kitchen scene is more likely to be a spoon than the shoe. In a semantic segmentations, pixel level labeling of the scenes for a precise understanding, each pixel is classified as a part of their objects or a background. For example, road, sky, building, etc. There are many techniques used. Some of them are CNN, convolution neural network, or RNN, or any graphics neural network. We call as a GNN, and even it will focus on the important detail of the scenes to improve the contextual retrieval. So we call as the attention mechanisms. As well as it will be representing object as a nodes and relationships as edges. For reasoning tasks, we call as the scene graphs. Next, it will combine the visual data with the textual, audio, or sensor data. For richer contents, we call as a multimodal learning. There are many applications. Some of them I can name it as autonomous driving to direct the roads, robotics, surveillance, augmented reality, smart cities, healthcare, context-based image retrieval. There are many applications over this. Still, there will be challenges in its scenes and a context understanding. That is the complexity of the real world scene. Many objects, occupations, and cluttered backgrounds make understanding the difficulty. Or the another challenges is the ambiguity. Similar looking objects in different scenes may confuse the model. Third one is a dynamic environment where the scenes changes over time. Example, moving people's vehicle requiring temporal understanding. Fourth one is a computational cost where the modeling relationships and context for large scenes can be resource intensive. To conclude this, the scenes and the context understanding extend the recognitions from the isolated object to holistic interpretations of the visual environment. By analyzing both objects and their relationships, machine can make informed context-aware decision essential for autonomous vehicle, robotics, surveillance, AR, VR, and many AI applications. So these are the topics we have covered in this. We'll move to the next topic. Next one is a recognition databases. In the database is essential for training and a benchmarking. So basically, it will be providing the label examples for the from the supervised learning in the machine learning models. So we have discussed about the image net, like a 14 image across a thousands classes. Here, the basic understanding of the recognitions of database is that from which data have been traveled, like Coco complex scenes from with multiple objects, or like a LFW, like benchmarks for face recognitions, Pascal VOC, like then so on. So these are the topics we have to be focusing on when come to the recognition databases. So basically, a test set is a collection of images or data that is separate from a training set and used to evaluate the performance of our recognition systems. Unlike the training set, the model has never seen the set test before, which ensure an unbiased measures of how well the systems can generalize to a new unseen data. So there are many classification for this categories of that. So to conclude this, the test sets and evaluation matrices are critical for assessing the performance and generalizations of the recognition systems. Like proper evaluations ensures that the models is not only accurate on a training data but can also handle the real world conditions from the accuracy and precisions to IOU map and ROC AUC. These matrices provides a comprehensive pictures of a system's performance across different recognition tasks, whether it is category recognitions, object detections, facial recognitions, or scene understandings. So these are topics we have discussed in this. We'll move to the next topic. Applications of image-based rendering. Here, image-based rendering is a computer graphics techniques that generates a new view of a scene directly from a set of images rather than relying slowly on 3D geometry. The IBR captures realistic appearance including the textures, lightnings, reflections, and making it is highly useful in the various fields. Just like AR VR argument, like telepresence and video conferencing, films and animations and video based rendering, gaming as well as. So the remote sensings and geometrical visualizations and even in a medical imaging conditions. There are many advantages in IVR in applications like photorealism, efficiency, flexibility, and cost efficiency. To conclude this, image based rendering is a powerful tool that bridges the computer visions and graphics, enable the creations of the photorealistic images and videos that captures from the data. So its application spans virtual reality, gaming, cultural heritage, and the remote sensing, making it essential for the industries where realism, efficiency, and user immersions are critical. So, in this, we have seen some of the topics related to the applications. We can move to the next topic. Applications of image recognitions. Image recognitions is a process of identifying object, people, scenes, or patterns in an image using a computer's algorithms, or modern systems often relies on deep learning for high accuracy. Its ability to automatically interpret visual data that enables a numerous practical applications. Some of the applications in healthcare, security and surveillance, autonomous vehicles, retail and e-commerce, as well as agricultures. When come to the manufacturing and quality controls, it also uses it to detect the detection, automation, sortings and classifications. It also used in entertainment and social media sites like documents and text recognition also. Even some of the advantage of image recognitions is that it reduces the manual inspections and monitoring and also can detect the subtle patterns not easily seen by the humans. The process large volumes of visual data quickly and also works in a various environment from factories to cities. So to conclude this, the image recognition is a transformation technology that powers modern AI systems across healthcare, security, retail, agriculture, etc., by converting the visual data into actionable insights. It enables a smarter decision making automations and improve the efficiency in numerous industries. So, I think we came to the end of this unit. We'll summarize the next part, then finish this unit. To have the summary of Unit 5, it covers image based rendering fundamentals like view interpolations and LDA for a scene synthesis. It also discusses about the recognitions as a visual understanding process and some of the category recognitions, facial recognitions, object deductions, and any ethics and privacy gaining importance, trends, realisms, application spans of the visions, graphics, as well as AI. So it's give an overall view about the perceptions, rendering, and intelligence of this unit. Thank you.